Hi, in this video, we will discuss what a buffer solution is, how to create one, how such a solution maintains a constant pH, and how to calculate the pH of a buffer solution using the acid ionization constant or using the Henderson-Hasselbalch equation. First, let me introduce the acid ionization constant. It is the equilibrium constant for the ionization of an acid. Okay, so let's say we have any acid represented by Ha. If we add that to water, this hydrogen will be given away to water to produce a hydronium ion. And the other ion is whatever remains of the original acid. So this A negative is produced from Ha. Okay, therefore they form a conjugate acid base pair, where Ha is the conjugate acid and A negative is the conjugate base. Now, based on this chemical equation, the acid ionization constant, represented by K sub A, is equal to the concentration of hydronium ions times the concentration of the conjugate base divided by the concentration of the reactant or conjugate acid. So that is again the concentration of hydronium ions times, okay, based on the chemical equation, we have the concentration of A negative divided by the concentration of Ha. Notice that in this equation or expression, water is not included. So the solvent is not included. In fact, in the numerator, we have only the product ions. So hydronium ion and the conjugate base. Okay, therefore, uh, the ionization constant, acid ionization constant increases when more acid molecules dissociate into ions. Now we know that strong acids are better at dissociating into ions, right? Therefore, for such acids, Ka, or the acid ionization constant, is greater than 1, whereas for weak acids, the acid ionization constant is less than 1. In this exercise, we have to write the chemical equation for the ionization of each given acid in water and the corresponding expression for the acid ionization constant. First, we have nitric acid. If we add that to water, this hydrogen will be given away to water since an acid is a hydrogen ion donor. That is to produce a hydronium ion. So from 2 hydrogen atoms, we now have 3. And the other ion is whatever is left of the original acid or the conjugate acid. So let's remove hydrogen, therefore we have NO3. Now since the nitric acid is neutral and it lost a hydrogen ion, so the charge of NO3 is now 0 minus positive 1, so that is negative 1. So this is the chemical equation for the ionization of nitric acid in water. Based on this equation, the acid ionization constant is equal to, let's multiply the concentrations of the product ions. So you have first the concentration of hydronium ions times the concentration of nitrate ions all over the concentration of the original acid or the conjugate acid. So that is HNO3. So again, in the expression for for acid ionization constant, water is not included. Okay, now let's consider hydrogen cyanide. Okay, so HCN. If we add this to water, this hydrogen will be given away to water to produce a hydronium ion. And the other ion is the remainder of the original acid. So that is CN. Let's remove, okay, the hydrogen atom. Now, since hydrogen cyanide is neutral, and it lost a hydrogen ion, so the charge of cyanide or Cn is 0 minus positive 1, so that is negative 1. And this is the chemical equation. Now let's write the acid ionization constant. So again, let's multiply the concentrations of the product ions. So you have first you have the concentration of hydronium ions, multiply that by the concentration of cyanide ions all over the concentration of the original acid. So that's HCN. Okay. Finally, we have acetic acid. Okay, so let's copy acetic acid, COOH. If we add that to water, by the way, remember in acetic acid we have this group, okay, which we call the carboxylic acid group. So in this group, this hydrogen will be given away to water. Okay, that is to produce a hydronium ion. And the other ion is again the remainder of the original acid. Okay, since acetic acid is neutral and it lost a hydrogen ion, okay, so the charge of this acetate ion is 0 minus positive 1, that is negative 1. Again, based on this chemical equation, let's write the expression for the acid ionization constant. So let's multiply the concentrations of the product ion. So you have the hydronium ion concentration times the concentration of acetate ions, COO negative, all over the concentration of the original acid. So that is the concentration of acetic acid. Then we also have the base ionization constant. It is the equilibrium constant for the ionization of a base. So let's say we have a base B and we add that to water. Since a base is a hydrogen ion acceptor, one of these hydrogen atoms will be given away to the base. That is to produce the conjugate acid BH. So since base in this case is neutral and it accepted a hydrogen ion, the charge of the conjugate acid is 0 plus positive 1, so that is positive 1. Now water lost a hydrogen ion or atom. Therefore, it becomes hydroxide. And since water is neutral and it lost a hydrogen ion, the charge of hydroxide ion is 0 minus positive 1, so that is negative 1. So based on this chemical equation, the base ionization constant, which is represented by capital K sub B, is equal to the concentration of conjugate acid times the concentration of hydroxide ion divided by the concentration of reactant or conjugate base. So that is the concentration of BH plus the times the concentration of hydroxide ion divided by the concentration of the conjugate or reactant base. Now notice that in this expression, water is still not included. And in the numerator, we have the concentrations of the product ions. Therefore, as more base molecules dissociate into ions, the value of the base ionization constant increases. And since strong bases are better at dissociating into ions, the base ionization constant for strong bases is equal to 1. Whereas for weak bases, the base ionization constant is less than 1. In this exercise, we have to write the chemical equation for the ionization of each base in water and the corresponding expression for the base ionization constant. First, we have bromide. If we add that to water, bromide is a base, so it has a tendency to accept a hydrogen ion. Therefore, it will accept one of the hydrogen atoms from water. That is to produce hydrogen bromide. which is the conjugate acid. Okay, since bromide has a charge of -1, okay, and it accepted the hydrogen ion, okay, therefore the charge of hydrogen bromide is 0, rather -1 plus +1, so that is 0 or neutral. Plus, the other ion is whatever is left of water. Since water lost a hydrogen atom, so it becomes hydroxide. And water is neutral, therefore the charge of hydroxide is 0 minus +1, so that is -1. So this is a chemical equation for the ionization of bromide in water. Based on this equation, let's write the expression for the base ionization constant. For that, we simply have to multiply the concentrations of the products. So concentration of HBr times the concentration of the hydroxide ions all over the concentration of the original base. So that is the concentration of bromide. Now let's consider carbonate ion. Okay, so carbonate, if we add that to water, it will also accept a hydrogen atom from water because it is a base. Okay, that is to produce H. Then let's copy the base, so CO3. Now this is bicarbonate or hydrogen carbonate. Since carbonate has a charge of -2 and it accepted a hydrogen ion, so the charge of bicarbonate is -2 plus 1, so that is -1. And again, the remaining ion is, the other ion is hydroxide ion. So this is the chemical equation for the ionization of carbonate in water. Okay, for the corresponding base ionization constant, let's do the same, okay, that we did for in part A. So let's simply multiply the concentrations of the products. So times hydroxide ion concentration and divide that by the concentration of the original or reactant base. Finally, we have methylamine. Okay, and this substance, NH2, is what we call amine, in which the nitrogen has a tendency to accept a hydrogen ion because it has at least one lone electron pairs. Okay, so let's copy methylamine. Okay, so if we add that to water, this nitrogen will accept a hydrogen from water. Okay, that is to produce CH3. Sorry, this one is NH2. Okay, so CH3, it becomes NH3 because it accepted a hydrogen ion or atom. Okay, so since methylamine is neutral, this one has a charge of 0 plus +1, so that's positive. Okay, and again, the other ion is hydroxide ion. So this is the chemical equation for the ionization of methylamine in water. Based on this chemical equation, the corresponding base ionization constant is, again, let's multiply the concentrations of the product. So that's CH3 and H3 plus times the concentration of the other product. So you have 0, concentration of hydroxide ion all over, yeah, the concentration of the original base, which is CH3, NH2. Now let's discuss what a buffer solution is. It is a solution that can resist pH change when the limited amount of acid or base is added. So how do we create a buffer solution? We simply combine a pair of weak conjugate acid and weak conjugate base. For the buffer solution to be able to maintain its pH, there should be appreciable amounts of the conjugate acid and conjugate base in the solution, at equilibrium. That is, in order for the conjugate acid present to be able to neutralize small amount of added base, and for the conjugate base present in the solution to be able to neutralize small amount of an added acid. A buffer solution works best when there are approximately equal concentrations of the conjugate acid and conjugate base. Here are some examples of creating a buffer solution. First, we can combine acetic acid with sodium acetate that contains the conjugate base acetate. In another example, we can also combine ammonia with ammonium hydroxide, which contains the conjugate acid ammonium. Now, we can also have a combination of carbonic acid and hydrogen carbonate, for example, in the blood of mammals, in which the pH should be maintained within 7.4 plus or minus 0.05. Now, how do we choose the substances and their quantities that we have to combine for a buffer solution? First, the pKa of the conjugate acid should be close to the desired pH. Now, recall that, as in the case of pH, the P in pKa means negative log to the base 10. So pKa means negative log to the base 10 of K sub A, or the acid ionization constant. And the value of that should be close to the pH that you want for your buffer solution. In a previous slide, we said that a buffer solution works best when the concentrations of the conjugate acid and conjugate base are approximately equal. So for comparable quantities of conjugate acid and conjugate base, the ratio of conjugate base concentration and conjugate acid concentration should be within the range 0.1 to 10. Now, one of the properties of a buffer solution is the pH range. So this is the range of pH that the buffer solution can maintain when a limited amount of an acid or a base is added. The pH range is defined as the pKa of the conjugate acid plus or minus 1 unit of pH. So, for example, the conjugate acid has an acid ionization constant of, let's say, 4.3 times 10 to the negative 6. So that is the Ka. First, we have to get the pKa. So pK sub A, hold on. pK sub A is equal to negative log to the base 10 of the Ka. So that's 4.3 times 10 to the negative 6. Let's calculate the value. Negative log 4.3 exponent negative 6. Okay, and that is 5.37. Okay, 5.37. Therefore, the pH range in this case is 5.37 plus or minus 1. Okay, so 1 unit of pH. Therefore, that is minus. So 4.37 and up to 6.37. So that is the pH range. Now, another property of a buffer solution is the capacity. It is the amount of added acid or base that can be neutralized so that the resulting pH does not go beyond, okay, the pH range. Okay, and the capacity depends on the quantity of the conjugate acid and base present in the buffer solution. Hence, we have to have appreciable quantity of the conjugate acid and conjugate base in a buffer solution. One approach to calculating the pH of a buffer solution is using the acid ionization constant Ka. To demonstrate this approach, let's consider this problem. We have 1 liter of buffer solution containing 0.0031 mole of carbonic acid and 0.031 mole of bicarbonate or hydrogen carbonate. We have to calculate the pH of the buffer solution using the acid ionization constant for carbonic acid, which is equal to 4.3 times 10 to the negative 7. This chemical equation shows the uh, ionization of carbonic acid in water. So you have carbonic acid. If we add that to water, one of the hydrogen in carbonic acid will be given away to water since an acid is a hydrogen ion donor. That is to produce hydronium ion. And the remainder of carbonic acid is HCO3. Okay, so we lost a hydrogen atom. Now, since carbonic acid is neutral, hydrogen carbonate or bicarbonate has a charge of 0 minus positive 1, so that is negative 1. Okay, so based on this chemical equation, the expression for the acid ionization constant is concentration of the hydronium ion, okay, hydronium ions, okay, then concentration of bicarbonate, so these are the products, okay, divided by the concentration of the original acid. Now, in this approach, we have to create an ice table. Okay, so we will use this table to account for the concentration. So first we have the initial concentration, then the change in concentration, okay, from the initial state to equilibrium. Okay, that is as the reaction occurs. Okay, so I see. Then for E, we have the concentrations, okay, at equilibrium. Okay, so let's account for the concentrations of carbonic acid, carbonic acid and the products, hydronium ions, and hydrogen bicarbonate. Okay, so initially we have 0.0031 mole, okay, per 1 liter. So remember the concentration that we want, by the way, is mole per liter. Okay, and that is in molarity. So 0.0031 mole divided by 1 liter, so that is 0.00131 molarity. Okay, for hydronium ion, initially, the carbonic acid and the bicarbonate ions, okay, have not reacted yet. Okay, therefore, no hydronium ion has been produced. Okay, so 0. Initially, for bicarbonate, we are given 0.031 mole per liter per 1 liter, so that is 0.031 molarity. Okay, as the reaction occurs or progresses from initial state to equilibrium, some quantity, let's say X, some quantity of carbonic acid, let's say that is the quantity X, okay, reacts with water, okay, to produce hydronium ions and bicarbonate. And what can we say about that reaction? Okay, so this is a balanced chemical equation, right? Okay, and we see that we have here 1, okay, 1 and 1. Therefore, for 1 mole of carbonic acid, 1 mole of hydronium ions and 1 mole of bicarbonate are produced. Okay, therefore, uh, yes, that quantity X of carbonic acid will be lost and will be converted into the same quantity of hydronium ions and the same quantity of bicarbonate. Okay, so these two, okay, denote that the same quantity of the products, okay, are produced. Okay, now at equilibrium, okay, for the concentrations at equilibrium, we simply have to add these two, okay, the first two concentrations. Okay, so for the carbonic acid, you have 0.0031 minus x. For hydroniums, you have 0 plus x, so that's positive x. For the carbonic acid, for the bicarbonate, we have 0.031 plus x, so that is the concentration at equilibrium. We will use this table in the next slide, okay, to answer the question in this problem. Okay, in the previous slide, we were able to write this expression for the acid ionization constant. But how do we get the pH of the buffer solution from that Ka? Recall that, okay, pH is defined as P. P represents negative log to the base 10, and H represents the concentration of the hydronium ions. Okay, so for us to be able to get pH, first we have to solve for the hydrogen ion concentration, okay, which we can isolate by cross multiplication. Of course, this is over 1. So we have Ka times times this denominator, okay, equal to 1 times this numerator. So that's hydronium ion concentration times bicarbonate ion concentration. Okay, so if we want to isolate this, okay, which we have here, okay, we have to divide both sides by this one. So that's why we have that here in the denominator. Okay, therefore the hydronium ion concentration is equal to this. Okay, so let's use that equation to solve for the hydronium ion concentration. Let's plug in the values. Okay, so we can get, okay, the values for these variables from the table. Okay, oh, sorry, it should be yeah, from the table, but we have to use the concentrations at equilibrium. So we will use the expressions in the last row. Okay, so equal to Ka, by the way, is yeah, Ka, the acid ionization constant of carbonic acid is given as 4.3 times 10 to the negative 7. Okay, times the concentration of carbonic acid. Carbonic acid, okay, that is ito, this one. So 0.0031 minus x, okay, all over concentration of bicarbonate. So that is this one. So 0.031 plus x. Okay, now we have to make an assumption. Okay, since the Ka, 4.3 times 10 to the negative 7, is a very small number, we can, hold on, where is the pen? Okay, yes, we can assume, okay, that x is also a very small value. Okay, such that we should be able to simplify this one into 4.3, okay, times 10 to the negative 7, okay, 0.0031 minus x, okay, x is a very small number such that we can assume that it is almost 0, okay, so therefore this expression, okay, can be simplified into 0.0031. It's as if we have 0.0031 minus 0, okay, all over Okay, we do the same for the denominator. Again, x is almost 0. So it's as if we have 0.031 plus 0, therefore 0.031. Okay, let's calculate this value. So the hydronium ion concentration is therefore equal to 4.3 exponent negative 7 times 0.0031 divided by 0.031. Okay, that is 4.3 times 10 to the negative 8. Hold on, where's the pen? Okay, 4.3 times 10 to the negative 8. That is the concentration of hydronium ions. Okay, so now we can calculate the pH. Okay, from this equation or formula. So we have pH is equal to negative log to the base 10 of the hydronium ion concentration, which we have calculated as 4.3 times 10 to the negative 8. Okay, and that is equal to negative log to the base 10 of 4.3 times 10 to the negative 8, 7.37. Where is the pen? Hold on, let me locate the pen. Okay. 7.37. Okay, and that is the pH of the buffer solution. Another approach to calculating the pH of a buffer solution is using the Henderson-Hasselbalch equation. So let's say we have, okay, any acid, HA, okay, if we add that to water, yes, a hydronium ion will be produced, and the other ion is the remainder of the original acid. So we have A negative. According to the Henderson-Hasselbalch equation, the pH of the buffer solution is equal to pKa. So this is the negative log to the base 10 of the acid ionization constant of the conjugate acid plus log to the base 10 of the ratio of concentrations of the conjugate base and conjugate acid. So we have pKa plus log to the base 10 of concentration of A negative over concentration of the original or reactant acid. Okay, so for this equation to yield accurate results, we have the following requirements. First, no strong acid or strong base must be present in the buffer solution. Okay, so we don't want any strong acid or strong base. Because remember, because in the first place, yes, a buffer solution should consist of a weak conjugate acid and a weak conjugate base. Okay, now remember for comparable quantities of of conjugate acid and conjugate base, we want okay the ratio of the concentrations of a conjugate base and conjugate acid to be within 0.1 to 10. And last requirement is that both the concentration of conjugate base and concentration of conjugate acid should exceed okay, the acid ionization constant by a factor of at least 100. So that is 100 or above. Let's consider some problems in using the Henderson-Hasselbalch equation. First, we have the same problem that we solved using the acid ionization constant Ka. So we have a buffer solution containing 0.0031 mole of carbonic acid and 0.031 mole of bicarbonate. We have to calculate the pH of the buffer solution using the Ka for carbonic acid, so 4.3 times 10 to the negative 7. And from the pH, we have to determine or calculate the hydronium ion concentration. Okay, so this one is the Henderson-Hasselbalch equation. To determine the pH of the buffer solution, we simply have to plug in the values. P is again negative log to the base 10. Ka is given as 4.3 times 10 to the negative 7 plus log to the base 10 of the concentration of conjugate base. So that is 0.031 mole per liter per 1 liter. So that's 0.031 molarity. But strictly speaking, this should be plus x, remember? 0.031 plus x. Okay. The X is the quantity of bicarbonate that is produced because of the reaction. But again, since Ka is a very small number, we can assume that X is almost zero, so we can ignore X. Therefore, we have here 0.031 molarity over, okay, the concentration of acid, of the conjugate acid, so 0.0031 mole per 1 liter. So again, we can ignore X, remember? So 0.0031. Okay, so let's calculate, okay, the value of this expression. So you have negative log to the base 10 of 4.3 exponent negative 7 plus log to the base 10 of 0.031 divided by 0.0031. So, hold on. Negative log to the base 10 of 4.3 exponent negative 7 plus log to the base 10 of 0.031 divided by 0.0031. So that is equal to, okay, we get the same value, which is 7.37. So that is the pH of the buffer solution. How do we get the hydronium ion concentration from pH? We have to use the reverse of the pH of the formula for pH. Remember, pH is equal to negative log to the base 10 of the hydronium ion concentration. And this is a logarithmic expression. Okay? To calculate the value of concentration of hydronium ions, okay, we have to use the inverse of logarithmic, which is exponential. Okay? And the corresponding exponential expression is that, okay, the hydronium ion concentration, okay, is equal to 10 to the negative pH. So let's plug in the calculated pH. So you have 10 to the negative 7.37. Okay, so the hydronium ion concentration is 10 exponent to the exponent negative 7.37. Okay, and that is 4.27 times 10 to the negative 8. Okay, 4.27 times 10 to the negative 8. Next, we have to calculate the pH of a buffer solution containing 0.035 molarity of acetic acid and 0.05 molarity of acetate. Acetic acid, okay, has a Ka of 1.8 times 10 to the negative 5. From the pH, we also have to determine the hydronium ion concentration. So once again, we have here the Henderson-Hasselbalch equation. For the pH of the buffer solution, we simply plug in values into that equation. So we have negative log to the base 10 for the P. Then Ka is given as 1.8 times 10 to the negative 5. Okay, plus log to the base 10 of concentration of conjugate base, which is the acetate. Okay, so we have 0.05 molarity. Okay, again, we can ignore the x, remember, because it is very small. It is close to zero. Okay, and for the concentration of the conjugate acid, okay, so we have 0.035. Okay, let's calculate the value. So that's negative log to the base 10 of 1.8 exponent negative 5. plus log to the base 10 of 0.05 divided by 0.035. And the answer is 4.899. So that is, we can round that off to 4.90. Hold on, let me locate the pen. Okay, 4.899 or 4.90. So that is the pH of the buffer solution. Now we have to solve for the corresponding hydronium ion concentration. And that is equal to 10 to the negative to the exponent negative pH. Okay, so let's plug in the pH negative 4.90. Okay, and the answer is, hold on, 10 to the exponent negative 4.9. Okay, 1.26 times 10 to the negative 5. Hold on. Okay, let me locate the pen again. Okay, so that is 1.26 times 10 to the negative 5 molarity. Finally, we have to calculate the pH of a buffer solution containing 0.25 molarity of nitrous acid and 1.25 molarity of sodium nitrite. Nitrous acid has Ka equal to 4.5 times 10 to the negative 4. From the pH of the buffer solution, we also have to determine the hydronium ion concentration. So for the pH of the buffer solution, we simply have to plug in values into this Henderson-Hasselbalch equation. So the pH of the buffer solution is equal to P is negative log to the base 10 times Ka is 4.5 times 10 to the negative 4 plus log to the base 10 of the conjugate base, which is nitrite, is in sodium nitrite. Now, for 1 mole of sodium nitrite, there is 1 mole of nitrite. Therefore, we can say that the concentration of the conjugate base is equal to the concentration of sodium nitrite, which is 1.25 molarity. So we have 1.25 molarity. For the conjugate of no, for the concentration of the conjugate acid, so that is given as 0.25. 0.25. Okay, let's calculate the value of this one. So you have so we have negative log to the base 10 of 4.5 exponent negative 4 plus log to the base 10 of 1, oh sorry, negative log to the base 10 of 4.5 exponent negative 4 plus log to the base 10 of 1.25 divided by 0.25. And that is 4.00457. Perhaps you can use 3 decimal digits, so 4.046. So the pH of the buffer solution is 4.046. Okay, so from that, let's calculate the hydronium ion concentration. Okay, so that is equal to 10 to the exponent negative pH. So let's plug in the pH. So we have 10 to the negative pH is 4.046. And the answer is, okay, let's input that in the calculator. Okay, 10 to the exponent negative 4.046. Okay, so we have 8.99 times 10 to the negative 5. So we can round off 8.99 to 9 times 10 to the negative 5 molarity. And that's it.